you very much, and many happy returns to not getting older. So I've given this talk several times, and it has unfortunately no relation to any work of Yuri I'm aware of, but still I think it is an interesting topic. Now, it is based on recent work with Yuval Filmos, Eldar Fischer, and my PhD student, Silvod Rakita. And there are two papers. There is a long paper, MC finiteness on restricted set partition functions, which actually was triggered by a question in Rakita's PhD thesis. And then there is a follow-up paper with Filmus, Fischer, and myself, effective MC finiteness. So here I give you an introduction to supercongruences as a legitimate topic in the study of integer sequences. So there is an overview. We can jump and so traditionally in combinatorics, there are many names for it, but C-finite sequences are sequences of integers. If there are constants P and Q, such that Ci and Ci coefficients in Z, such that for all n bigger than Q, the linear recurrence relation Sn plus P equals a linear combination of the previous P elements holds. C-finite sequences are also called in the literature constant recursive sequences or linear recursive sequences, and they have been studied for ages. They have limited growth. I'm not giving the best possible result, but an is almost smaller than 2 to the Cn, where C is any constant suitable for the sequence. Actually, a lot more can be said, but we don't need it. Now, an MC finite sequence, which by this name I introduced some time ago, but it goes back to work by Specker from the 80s, is the same as a C-finite sequence, but you fix it modulo M, and it holds for every M, but with different coefficients and parameters. So C-finite sequence, there are constants P depending on M and Q depending on M, such that for every n bigger than Qm, there are linear recurrence relations, and the coefficients C are also dependent on M, such that for the M particular M, the recursion holds modulo M. If you are given a sequence, you will give me a sequence Cn, I denote Cm to the upper M, the same sequence modulo M. So there is a little observation which turns out to be not as trivial as you expect. The sequence Sn is MC finite if S upper M, n is ultimately periodic for every M, where the periodicity depends on M. MC finiteness implies periodicity. This is an exercise, but the converse was proved by Reitz and Sloan in '85 and is a slightly more sophisticated statement. Can one move this green thing up because I don't see my own?
This one you want to move back.
Yes.
Sorry.
Very good. Thank you. Okay. Now we observe that there exist MC finite sequences an such that a function which given m and n gives me the value of the sequence an modulo m is not computable from n and m alone. So this is in contrast to C-finite sequences. And the proof, I can only sketch it. Let Bn be a non-computable 0-1 sequence, and let Pn be the sequence of primes. Then we can use the Chinese remainder theorem and do some magic. And then we look at the sequence an equals p of k modulo pk to the n, and using, we can see that this is MC finite, and it is not computable because we plugged in a non-computable sequence at the beginning. So the motivation for looking at these MC finite sequences is the question is, given any sequence, you have this interactive databases on integer sequences, you pick your favorite or randomly a sequence out of these databases, and you want to know whether it is MC finite. So what do we have to know to establish that the sequence is MC finite? And in case it is MC finite, what do we have to know in order to compute it, the modular version of the sequence efficiently? Now, computing Sn modulo m is useful in order to falsify a claim that S of A equals B in case B is very big or even not big, and obtain the computer program for such weird computation. We just check it modulo. Now, this is Specker found it like this because, well, I don't tell you.
Motivate what? Looks like you motivate MC finite. But I mean,
No, I'm asking questions, but I give you a motivation now. Just let me talk. So Specker was teaching topology to students in the third semester when it was still fashionable to teach general topology. But being a logician, he also gave them exercises on computing the number of finite topologies on an element set, and they did it by hand for 1 and 2 and 3 and 4. And then he challenged them and he said, can you do it for 5? And one student went to the library using all the tools of librarian research, and he found 2 papers with different results. And Specker felt very, very challenged and saying at least one should have a method of deciding that one of them is truly false. And then he devised all this machinery which I give you now. But this was actually for small values. But indeed, you can implement such, if you have established MC finiteness and an algorithm, you can implement this, and you can now pick, somebody gives you a program, I have a way of computing the number of primes between 1 and n for very, very big values, or something similar, of which you know it is MC finite, and then you can challenge the value and falsify it. So there are some closure properties. MC finite sequences are closed under various arithmetic operations, like multiplication with a constant, addition, multiplication. If additionally Bn tends to infinity, then also An to the Bn is MC finite. And let An be a subset of natural numbers, be non-periodic, and An equals 2 be a constant, hence MC finite sequence. Let Bn the sequence Bn equals 1 for n in A and n factorial plus 1 otherwise, then Bn is MC finite and oscillates. However, An to the Bn is not MC finite. Now, if you Google supercongruences, you get an answer which is not what we need here. But recently, Banderier and his friends had a paper where they call a relation super congruence, then if it is MC finite, no, not for every m, but for a subset of n. So this is different from the original definition of supercongruences of S of np equals sp modulo p to the r. But I think it's a very suitable name. So we use supercongruence in the latter sense. Hence, the sequence is MC finite if it satisfies a supercongruence where m is all the integers. Clearly, if a sequence Sn is C-finite, then it is also MC-finite with Rm equals R and Cim equals Ci for all m. We shall see that the converse is not true. So let's look at some examples, and the two red ones I give here will establish that there are uncountably many of those. So the Fibonacci sequence is C-finite. This is the first, the mother of all C-finite sequences. Sn is C-finite, and it is at most exponential, I mentioned before. The Bell numbers are not C-finite, but are MC-finite due to a growth argument. And let Fn be an integer sequence and multiply it by 2, then is ultimately periodic modulo 2, but not necessarily MC-finite. Now let Gn be any integer sequence and multiply it by n factorial, then it is MC-finite trivially. So we have uncountably many MC-finite sequences. The sequence S3 of n, half of 2n, choose n, is not MC-finite. The value is odd if n is a power of 2, otherwise it is even by an observation is attributed in the literature to Lucas, but wasn't published at that time. The Catalan numbers have a similar form, 1 over n plus 1, 2n choose n is not MC-finite since Cn is odd if n is a Mersenne number, and ultimately let P a prime and Fn a monotone increasing sequence, then Sn defined as P to the Fn if n is different from P to the Fn, and defined as P of to the Fn plus 1, otherwise is monotone increasing, but not ultimately periodic modulo P, hence not MC-finite. And as we again choose arbitrary sequence to produce this example, we get uncountably many MC-finite and non-MC-finite sequences. So how many there are? Well, I mentioned now from the examples, there are uncountably many monotone increasing sequences which are MC-finite, and there are uncountably many monotone increasing sequences which are not, which are MC-finite but not computable. We also can show that MC-finiteness is rather rare. Proposition 6, with respect to Lebesgue measure, almost all integer sequences are not MC-finite, and we have to do some manipulation how we use this Lebesgue measure. So here is a brief history of this subject. It was introduced when I was working on Specker's result, and I coined the name MC-finite because I lectured in a seminar and we liked this name. Without its name, the concept appears in Christian Blatter and Ernst Specker in 81 for the first time. Otherwise, it rarely appears in the literature under the name supercongruence. However, under the name supercongruence, it appears in the paper by Banderier and his friends in 2017. The 4 substantial monographs on integer sequences published after 2000 do not mention the concept at all, not even under a different name. And just to make some propaganda, there are 4 books I count among those, recurrent sequences by Everest, Van Porten, Sparlinski, and Ward, analytic combinatorics by Flageolet and Sedgwick, combinatorics of sets partitions by Mansour, Tufik Mansour, and combinatorics and number theory of counting sequences by Istvan Meze. So in some sense, I also talked to people about it. They always found some theorems I mentioned by Specker very interesting, but it didn't catch on. The fundamental references for what I talk about here is a paper by Blatter and Specker in the full version from 84, more didactic exposition of Specker alone from 90. My recent paper with Eldar Fischer, Extensions and Limitations of the Specker-Blatter Theorem from 2022. And Kodiak, Mazowiecki, Pepperman, Pilipchuk, and Seni Selek on polynomial recursive sequences from 2020. So we have a definition, we have a claim for an application, and now how do you verify that the sequence is MC finite? And it's preferably, how do you verify it? The method which gives you infinitely many applications, not just one brute force application. So given an integer sequence, we look for a proof which shows that Sn is MC finite and from which one can extract an efficient algorithm to compute a modular version of the sequence. There are two such proof methods which exist in the literature, restricted classes of MC finite integer sequences. One model theoretic, which goes back to Blatter and Specker of 81, and a method based on polynomial recurrence relations due to Bandelier, which is more recent. We notice that so far there is no general algorithm to establish that the sequence is MC finite, which applies to all cases. So how we do it in model theory, Specker and Blatter found a very powerful model theoretic method to prove MC finiteness, the Specker-Blatter theorem. It uses definability in monadic second-order model logic, and it says the following: let S phi is a formula of n, be the number of binary relations R on a set 1 up to n, which satisfy a given formula phi in monadic second-order logic. The sequence S phi of n is MC finite, or equivalently, Sm is ultimately periodic for every n. Now, the original Specker-Blatter theorem was stated for classes of structures with a finite set of binary relations. In 2003, Fisher showed that it does not hold for one quaternary relation, and very recently, Fisher and I showed that it doesn't hold for at least even one ternary relation. Just if you don't have an example in mind, I come later to it, but counting the number of partitions, Bell numbers satisfy this hypothesis. Counting the number of transitive relations satisfies this hypothesis, and we'll see many more. Now, Specker introduced a rank, which I call here Specker rank, of a formula monadic second-order logic phi, and it's a semantic parameter of finite models of phi. Specker rank phi can be shown to be finite provided phi is a formula in some extension of monadic second-order logic, but this is algorithmically tedious and gives a very bad upper bound. Sometimes the rank can be determined by looking at the models of phi, and in applications, one can often see that phi has very low Specker rank, though if you use the abstract theorem, which covers all formulas, it includes the worst case and has a very bad performance. Example, if all the models of phi are connected graphs, the Specker rank is 2, but if you use a formula and you want to derive the Specker rank by simply using the syntactic form of the formula, you get the result, but it's much bigger than 2. We conclude that we conclude that given the Specker rank n and m, then this can be computed in linear time. But then we are left with the problem how to compute the Specker rank. Proving that the class of graphs is MSOL definable may be immediate or very difficult. The following are typical examples. Define a finite set of forbidden subgraphs or induced subgraphs is first-order definable. Planar graphs is monadic second-order definable using Kuratowski theorem. Graphs of genus G are monadic second-order definable using an observation by Courcelle based on Seymour and what's the other name? I have a gap in my memory. Robertson. It's also true for all minor closed graphs, and in particular graphs of tree with at most k are monadic second order definable. Eulerian graphs are not monadic second order definable, but are seen counting monadic second order definable is modular counting quantifiers, where it also holds. So here is a picture of Specker, who was my most influential teacher in logic, and Blatter, who was my most influential teacher in calculus and didactics. They both passed away only recently. And they have 4 papers I mentioned already. It's a lesson because before I started working on an open problem, they left the citation index gave at most 10 citations or even less, including their own. And so it was kind of completely overlooked, but because it was published in the wrong places. So this is something to tell your students, that you should be careful with where you publish. Now we look at the following versions of transitive relations, which appear in the online encyclopedia of integer sequences. The number of equivalence classes are Cabell numbers, the number of linear quasi-orders, linear pre-orders, the number of quasi-orders or pre-orders, the number of partial orders, and the number of transitive relations Tn. They are all definable in first order logic, and we have some estimates how they are, but for none of them there is an explicit, well, the Bell numbers are reasonably well studied, but there are no explicit formulas where you can derive an immediate, even a slow algorithm which proves this. So here the theorem is extremely powerful, because you immediately see that it is first order definable, hence by Specker-Blatter it is MC finite. Now the other method you can prove MC finiteness is using polynomial recurrences. And already in Specker's paper from 90, he notes the following: in many cases, in many known cases, MC finiteness of a sequence Sn is a consequence of polynomial recurrence relations where Pi are polynomials over Z. For Sn n factorial, this is obvious. In general, this needs some more elaboration, and indeed Specker didn't prove it. He just noticed that in many cases this is the case. Now, how to prove it using polynomial recurrences? An integer sequence Sn is holonomic over Z if there exists polynomials Pi over Z with P1 up to Pk different of 0, such that Sn is not a linear recurrence but a polynomial recurrence over n, and integer sequences are polynomial recursive over Z if the same holds, but you have a sequence of, or a set of recurrence relations which use mutual recurrence. If Sn is an integer sequence which is polynomial recursive over Z, then Sn is holonomic over Z. And inspired by the work of Kadiak and his friends, we prove Sn is an integer sequence which is polynomial recursive over Z, and n, then Sn is MC finite. In particular, this is true also for integer sequences Sn which are holonomic over Z. But you have to be careful. In general, holonomic sequences are defined over fields rather than a ring Z, and they are sometimes also called T-finite and P-recursive, and Kadiak defines polynomial recursive for rational numbers rather than integers, and the polynomials are over Q. In both cases, one can prove weaker forms of supercongruence, but to get MC finiteness, the restriction to be over Z, what did I do? Over Z is needed. So here are examples of polynomial recursive sequences, which are all taken, except the last one from Kadiak's paper. The sequence an equals n factorial as a simple recurrence is holonomic and obviously is MC finite. The sequence an equals 2 to the 2 to the n is polynomially recursive, a0 equals 2, and an equals a of n minus 1 to the power 2. It is not holonomic, since Gerhold showed that every holonomic sequence is bounded by some 2 to the pn for some polynomial p. It is easy to see that an times 2 to the n is MC finite, but is also MC finite by the Specker-Blatter theorem below, as it counts the number of ways one can interpret a unary predicate over n. The Catalan numbers are holonomic with the recurrence relation n plus 2 times Cn plus 1 equals 4n plus 2 equals Cn. They are not holonomic over Z, since they are not MC finite. Furthermore, they are not polynomially recursive, even if you allow rational numbers. A sequence n to the n is not polynomially recursive, but it is MC finite by the Specker-Blatter theorem, because it counts the number of functions of n to n. We show that in our paper that the sequence A08714, given by the equation A of 0 is 4, and A of n plus 1 is an choose 2, is not MC finite, but is periodic modulo every odd number. Test problem for you can give to your students. I don't have students anymore, so this is for which integer sequences fn and gn is the sequence Sn 1 over fn times gn choose n, not MC finite. This is the case for Catalan numbers and very likely for infinitely many cases which are minor variations of the Catalan numbers. So how can we compare the two methods? If one proves MC finiteness for integer sequence directly, the proof may be sometimes straightforward, but it's also sometimes very tricky and likely not applicable to other cases. In contrast to this, the Specker-Blatter and the other theorem are meta-theorems. They only require to check for some structural data about the sequence, whether they satisfy these restrictions or recurrence relations or logical definability. But this this applies then to the most general case, and in both cases gives very, very bad bounds. And on top of it, it may also be difficult to establish whether it is definable in monadic second order logic, or whether you get a set of recurrence relations, etc. We note that the two meta-theorems cannot always be applied to the same integer sequences. So let's compare. The sequence n to the n counts the number of unary relation as a binary relation from n to n, which is first order definable. It's easy to find out. But n to the n is not polynomially recursive, as shown by Kadiak in their paper. However, MC finiteness can be established directly without much effort. The sequence we have given before satisfies an equals 2 to the 2 to the n. This is polynomially recursive sequence over z, which grows as fast as 2 to the 2 to the n. However, counting the number of k binary relations over n is bounded by 2 to the k to the n square, hence theorem cannot be applied. Again, MC finiteness can also be established directly without much effort. So I'll finish here almost. I just give you, to show off the methods, I give you a sample list from the online encyclopedia, which I looked at. And blue means it is MC finite by Specker method. Cyan color is by the extension of the Specker method, which we established. Red, it is not MC finite, and green, it is still open. So the Catalan numbers are not MC finite. They can also be established as non-crossing partitions. Bell numbers are MC finite. Stirling numbers of the second kind are MC finite. And there is a funny thing, Upuluri Carpenter numbers, never mind what it is, you can look it up, are MC finite using the extended method. Number of linear quasi-orders, partial orders, law numbers, which is another variation of this, are MC finite using Specker-Blatter. Number of B-colored partitions uses the extension. R Bell numbers. These are Bell numbers where the partitions you fix was established in, I think, in statistics originally. You look at partitions where a fixed number of R elements have to satisfy certain properties, like to be in one particular block of the partition, or so on. R Bell numbers, where are they? Wait. A2, and R Bell numbers for bigger numbers also. Number of transitive relations. Now the Bessel numbers, Bn to the power of B, are number of non-overlapping set partitions. This is still open. We couldn't establish either of the two. What did I say? Red is not. So this function I mentioned before, An choose 2, is not MC finite. Regular labeled graphs of degree 2 and 3 are MC finite. Stirling numbers are, etc., etc. And the regular labeled graphs, but without bound on the arity of the edge, R is still an open problem. So I invite you to read the two papers I mentioned. And here again are the pictures of the contributors. Thank you very much.